Have you ever wondered about the fate of our universe? Are we doomed to end up in the Big Crunch when the entire space will collapse to just one point? Or maybe we will eventually be blown up by the expansion? In fact, humanity will probably go extinct before all the dramatic occasions. However, there are some aspects we can already predict, and today I invite you on this fascinating journey. Welcome to my presentation on the 2011 Nobel Prize for the Accelerating Universe. Let me first make you familiar with the outline. I will, of course, start with a brief introduction to this broad topic. After that, we will go through the historic series of experiments that made it possible to perform the study. I will predominantly concentrate on the experimental part, such as the setup and error sources. And lastly, I will point out related theoretical and observational aspects. To begin with, I'd like to explain what the expansion of the universe actually means. It is quite common to think that the objects are flowing away from each other. Nevertheless, this idea does not describe reality appropriately, or at least may lead to faulty description. What is happening can be easily illustrated with a simple classical demonstration. So let's say we have a balloon and we put some dots on this balloon that represent galaxies or other cosmic objects, and we also paint a grid there to feel the scale. All the lines and points are obviously attached to the balloon, they have a fixed position, and they are not able to move. However, when we start to inflate the balloon, we may see that the points are now situated further away from each other, albeit non-moved. This is because the spaces between them grew. Mathematically speaking, it is the metric of the spacetime that expands. And people also wanted to know how fast did the expansion happen. A series of experiments conducted throughout history tried to make the estimate as accurate as possible, and the scientists whose portraits you see in the slide expected to measure the expansion rate, of course, and observe one of the two scenarios. Either the universe should first expand and then contract, or its expansion should happen very slowly and even slow down over time. What they discovered instead was like throwing a ball up in the air and then having it fly away into the sky rather than getting it down by gravitational attraction. Not only wasn't the expansion rate slowed down by gravity, but it was also accelerating. To show this explicitly, I will first go through some basic cosmological concepts. To describe the expansion rate, one usually defines the quantity called scale factor and is denoted by A. It is simply a quantity that shows how much the distances changed due to the inflation of our balloon, being a relation of the scaled length to the unscaled one. From this definition, we can easily derive the Hubble's law. This elegant equation introduces the so-called Hubble constant, or Hubble parameter, that describes the expansion rate. Although called a constant, it is rather a function of time. We call it a constant only to highlight that it is independent of spatial coordinates, and the expansion happens simultaneously at all points. The value of the Hubble parameter we measure today is around 70 kilometers per second per megaparsec. These strange dimensions simply mean that at 1 megaparsec distance, all objects are seemingly flowing away from us at the speed of 70 kilometers per second. The farther the object, the faster we see it flowing away. But how do we measure the expansion? We use something called redshift. When a faraway cosmic object emits light, the wave travels to us for many years, I'd even say millions or billions of years. As long as the universe continues expanding in the meanwhile, we observe somewhat longer waves with scaled wavelengths. And the relation of the observed and emitted lambdas defines the redshift. The initial wavelength is usually extracted from the spectral lines of the matter content of the object. And the observed one is, well, the one we observe. Long story short, the redshift is directly related to the scale factor and therefore to the expansion rate. The scale factor today is chosen to be 1 just for convenience. So how can we find the expansion rate? Once again, we remember that Hubble's law expresses the relation between the velocity and the distance. At the same time, The velocity is related to the redshift. Note that this is just a sample formula from special relativity. In fact, we sometimes must use some more complex equations, but it illustrates that there is some relation. Thus, if we measure the redshift and the distance to the object, we may find the expansion rate. The first person to come up with this brilliant idea was Edwin Hubble. However, he got a bit higher value of around 500 kilometers per second, the megaparsec instead of 70. The main issues of his approach were the usage of the special relativity formula I just showed and the problematic calibration of distance measurements. Talking of distance measurement calibration, nowadays we have many methods to measure distances, each suitable for a specific range. However, when we invent a technique to go further in our measurements, we always have to be sure that our new method gives the same result as the previous one at the distances that work for both methods. That is why we obtain the so-called cosmic distance ladder. We cannot proceed to the next ladder rung if we do not step on the previous one. I will briefly introduce the distances we already went through so that you see the evolution. As mentioned, the expansion rate depends on the separation we measure it at. That is why we have to get somewhere here to see the expansion rate clearly. So the first method for the nearest object is radar ranging, which is quite self-explanatory. Astronomers transmit, receive, and analyze the reflected waves to extract the position of the target. Eventually, the distances go beyond the radar's range, and we have to create something new. When we, let's say, travel to nearby stars, our principal tool is a parallax. This is a simple geometrical method which takes about half a year to use. As we orbit the Sun, the position of the nearby stars will apparently shift slightly, giving us some angle. Knowing that the distance between our June and December position is 2 radii of the Earth orbit, or 2 astronomical units, we may infer the separation between our planet and the star. At some point, the angles become too small to be measured, and we have, again, to move further. To reach the size of the entire galaxy, we use the main sequence fitting. Main sequence stars are those undergoing, so to say, typical and well-studied evolution. These stars fuse hydrogen into helium, and their color depends on the fraction of this element, or better said, on the fusion stage. This diagram shows the relation between the color of a star and its real brightness, also called intrinsic luminosity in a smart and fancy way. When we also measure the apparent brightness, we may calculate the distance to the object. As the distance is enlarged, the luminosity decays dramatically. For example, the Milky Way is about 40,000 parsecs, and at this distance, the stars appear roughly 15 orders of magnitude fainter than they are. Imagine we are now drawing in further away. The stars get so faint that it is no longer possible to perform a main sequence fitting. What can one do next? An intermediate step between the distances we need and the main sequence fitting uses Cepheids. They are essentially periodically pulsating stars of different sizes and colors. Nevertheless, the period of their pulsation is directly related to their brightness with this beautiful formula. And after we know the brightness, we may infer the distance with another beautiful formula from the same reference. At the distances that we need to see to measure the expansion rate acceleration, Cepheids are no longer visible, but they allow us to proceed to the final and crucial step. The bright objects used in the measurements are type 1a supernova. During a few weeks after the explosion, a single such supernova emits as much light as an entire galaxy. Essentially, this type forms in the following way. When a star runs out of all light atoms and only carbon and oxygen remain at its core, the white dwarf forms. You may see them on this diagram in a separate region. This star is very compact, of approximately solar mass and Earth's size. More often than not, a white dwarf is a part of a binary star system. Here is a photo of a Sirius binary with a white dwarf as an example. You may see that it is extremely small and faint. Even so, its gravity is strong enough to, let's say, steal the gas from its companion star. And when the white dwarf reaches a Chandrasekhar limit, which is around 1.5 solar masses, the interior of the dwarf becomes so hot that runaway fusion reactions start. The star explodes with a brief emission of strong radiation caused by nuclear fusion products. Most supernovae have very similar spectra and light curves, which make them very convenient for distance measurements. The type 1 supernova possess very sharp and distinct explosion light curve peaks, which may be seen in the slide. To further classify them as type 1a supernova, their unique spectral features are used: the absence of hydrogen and the presence of silicon absorption lines. So now, as we know what objects we deal with, we may proceed to the experiment that led to the discovery. First, we need to find a type 1a supernova to be able to use it. Back then, people could not predict the upcoming explosion, so they presumably had to monitor the entire sky to not to skip one. Moreover, explosions happen only a couple of times per millennium in each galaxy, so one needs great luck to spot them. But that's just me scaring you a bit. The 1A supernova occur in all types of galaxies and at different distances from us, so they are not that rare and possible to notice. The Supernova Cosmology Project group, led by Saul Perlmutter, created a strategy dubbed Supernova on Demand. They used a CCD-based telescope with great resolution to observe thousands of galaxies over 2 to 3 nights just after the new moon, imaging the same patches of the sky like after the new moon and then 3 weeks later. This allowed them to detect dozens of new supernovae. After a potential supernova discovery, its spectrum was analyzed to confirm the guess. Here, I would additionally note that the peak luminosity of a supernova occurs shortly after the explosion. Therefore, a supernova must be observed early on so that the peak magnitude is determined with high precision. The timing ensured that at least some of the supernova would be in that phase. And after 7 or so years of research, around 40 suitable explosions were spotted. So, as we are now sure that we found the type 1a supernova, we may aim to extract its emitted and measured luminosity. However, the observed brightness of a supernova may be affected by different factors, such as dust extinction, intrinsic variations, actually stretching of supernova light curves due to the expansion of the universe. And to account for all these factors, the trip calibration method was used. Shortly said, this technique involves the comparison of the newfound supernova brightness with well-calibrated, so to say, local type 1a supernova. Let's go through the trip calibration description step by step. The first stage is basically a selection of the reference sample of local type 1a supernova. These are essentially supernova with an accurately determined intrinsic brightness. Various techniques are generally used, often involving the previously mentioned Cepheids or other rung of the cosmic distance ladder. This way, we get a well-known dependence of the observed brightness over time. In the second phase, we must match the light curves of the local calibrators with those of distant supernova. The latter are stretched or compressed so that they align with the local calibrated ones in shape and duration. After that, the so-called distance modulus mu is calculated. This quantity depends on the stretching or compression coefficients, which we found at the previous stage, and this distance modulus is simply defined as a difference between the observed and intrinsic brightness of a distant supernova. So on the other hand, and that's what allows us to infer it. And finally, the distances are calculated using the freshly found distance modulus. It is also important to keep in mind that not all type 1a supernova have the same intrinsic color. This implies further corrections for the reddening effect, which I'll explain in the error sources part. For now, it's enough to realize that the luminosity is different for different colors, and this fact provides us with further information on the content, temperature, etc. And that also means that we have to perform many luminosity measurements. To successfully determine the expansion rate, we must also measure the redshift, as said before. By observing the supernova's light in different wavelengths, we may see how the spectra of the elements were changed while traveling through the universe. After all the mentioned procedures, we may finally calculate theoretical predictions and perform some comparisons. The laureate team plotted the brightness parameter against the redshift of numerous supernovae, along with the theoretical predictions for different cosmological models, which parameters you see on the right, and I'll describe them a bit later, because there are lots of points I'd like to highlight first. So let's concentrate on the horizontal axis to begin with. There we may see what were the redshifts of different supernovae involved in the study. And they are denoted with red points, and also some previously observed supernovae with yellow points. These redshifts correspond to certain scale factors, meaning that these objects' spectra were stretched from 2 on the left to 50 on the right percent. That is to say, for distant objects, we got the 1.5 times bigger wavelengths than they were initially. In other words, when this supernova exploded, the universe was 2 to 50% smaller. Here you may also see that we may calculate the distances from that. Note that I put approximate ones. Here, I didn't stress that the light travel a bit nearer than the distance currently is. The reason for that is that the length enlarged in the process of traveling. And furthermore, I put here the approximate age of the universe at the time the light was emitted. Nowadays, it's 13.77 giga-years old, so just slightly, so to say, older than the most left number here. All these numbers are here for you to feel the context and the scales. Second, we may notice that up to some values, the depicted relation is almost independent of the cosmological model we assumed. We start feeling the difference at around 1 gigalight year, so when the red points begin, let's say. And yeah, we also see that is the difference between the models is best noticeable at 10 gigalight years. And if you recall the cosmic distance ladder I showed at the beginning, we may see that we indeed had to reach the last stage here to be able to test the models appropriately. The closer distances would not give distinct results. So let's now concentrate on the parameters of the cosmological models mentioned, so that we can understand the result, or better said, the consequences of the experiment for the science. We mainly consider 4 parameters in standard cosmology. They characterize the ratio of matter, radiation, curvature of the universe, and the so-called lambda term. These omegas are simply the fractions of these essences, and together they must make up 100% or a 1. To make it more clear, I'll briefly clarify the jargon used. Under matter, we understand all non-relativistic matter we have, including dark matter. Radiation is in turn a relativistic matter. It includes massless or nearly massless particles such as photons and neutrinos. Nowadays, there is very little relativistic matter left. In other words, the average matter is non-relativistic. To realize that, we may do simple calculations. So let's take the room temperature as a defining point. It corresponds to some millivolts of particles' kinetic energy. At the same time, the mass of the proton, which is the lightest baryon, is 10 orders of magnitude bigger, and even the lightest leptons, excluding neutrinos, of course, are a million times larger. This means that already at room temperature, the matter is almost entirely non-relativistic. And note that the temperature of the universe, if I'm allowed to say that, is 100 times smaller than the room temperature. Hence, we may put the omega of radiation to 0. In fact, the constraints and omega radiation is 0.01, which is, well, approximately 0 in our context. Then the curvature just defines the form of the universe, which also effectively contributes to its content. Better said, it influences the dynamics. The curvature omega is positive for a spherical, or also called closed universe, 0 for a flat, and negative for a hyperbolic or open one. Finally, the lambda term is a mysterious form of matter, sometimes called dark energy, that has negative pressure and is a driving force of the expansion. Originally, Einstein included this lambda term in his equation to make the universe static, but later, after its expansion was discovered, he admitted that it was the biggest mistake of his life. Today, however, the lambda term is restored while serving the exact opposite purpose. We use it to describe the accelerated expansion of the universe. That is to say, the absence of lambda means a decaying expansion rate for us. So you again see the parameters of the model to the right. The black text and plots mean the decaying rate, as I already said, because here we put lambda to 0, and that means we do not have any force that drives the accelerating expansion. You may see that the only black line that comes close to the experimental data is the one with unrealistically empty universe with no matter. However, we do know there is matter in the universe, and in fact, quite a lot of it, which makes this model basically unfit. At the same time, the flat universe models with dominating dark energy seem favorable. Indeed, the most widely accepted model today is 0.3 omega matter and 0.7 omega lambda, which lies between the highest two blue lines, so between 0.5 and 0.1. And we see that it indeed goes very close to the experimental data. Therefore, the study concludes that we must live in an accelerated universe with a great fraction of dark energy, and this universe is most likely flat. Yeah, I'd also like to describe the systematic error sources that authors estimated in their work. The first one would be the dust extinction. As said, supernova are found in different galaxies, and the galaxies are filled with microscopic matter, which we refer to as dust. For instance, the beautiful pictures of the night sky are due to the light scattering of the Milky Way and also Earth orbit dust. The scattering makes objects appear fainter. In addition to that, just as regular dust, it partly absorbs the light, meaning that we must not only account for the natural dimming due to the large distance, but we also have to include the fading because of this absorption. What makes it even more complicated is that the amplitude decrease strongly depends on the orientation of galaxy. As in this example, if the light travels to us along the red arrow, it encounters more dust in its way, and the spectra will be distorted more. To evaluate the spectral deformation, one should know that different wavelengths amplitudes change differently. In particular, blue light gets absorbed faster, which causes the apparent reddening of the objects. Knowing this, one can see how the proportions of the different wavelengths changed compared to the emitted light and estimate how much of it was absorbed. The next contribution is a collective, including various biases involved in the study. It was evaluated that the most significant is the Malmquist bias, which refers to the overrepresentation of intrinsically brighter objects. This is because the apparent luminosity of an object decreases with distance according to the inverse square law, and as a result, intrinsically brighter objects tend to be included in a sample preferentially, leading to an overestimation of their average luminosity or distance compared to the true underlying population. Perlmutter estimated it to be less than 4%, which is, well, not that significant to change the suggested cosmological parameters. The other luminosity biases, such as, for example, host galaxy bias, which suggests that supernova from certain galaxy types may be underrepresented, affect the experiment even less. Another possible important bias would be the evolution bias. It emphasizes that the evolution of supernova may change as the universe ages, suggesting that their luminosity may differ from that of local supernova, which makes the trip calibration not a very good method, in fact. The uncertainties here lie below 1 sigma, but are considered large enough for the subsequent tests to be needed. Finally, some supernova may be observed through overdense regions, and the gravitational lensing would make them appear brighter. With a large enough sample, this effect averages out, and because we also know that some supernova in turn are observed through underdense regions. So for all the precise calculations and analysis done, I strongly encourage you to see the paper, because otherwise it will take really loads of time to describe each method specifically. Now a few words about the explanations of the phenomenon. As already mentioned, the most widely accepted theory is the dark energy, or the lambda term, which tells us that there is some essence with a constant or nearly constant density. So as the universe expands, the matter density becomes smaller, and the fraction of dark energy grows in turn, making the expansion accelerated. There are also some less famous variations of this theory, and even some attempts to unify dark matter and dark energy into one dark fluid. The main source of skepticism here is that we actually have to introduce a type of matter with negative density, which does not sound very appealing. With negative pressure, of course. Then the second most widely used approach is modifying gravity. It involves adding new terms to the Einstein-Hilbert action in general relativity, or attribute graviton non-zero mass. However, modification of the GR action usually does not fulfill either the solar system tests, so to say local tests, or the accelerated universe experiments, or even both at the time. Moreover, one has to argue the corrections they make, which is quite problematic. As for the graviton, both massless and massive particle theories are pathological. So some less popular explanations include the repulsive gravitation of antimatter, which is not likely to cause such an acceleration due to a relatively small amount of antimatter compared to matter. The back reaction conjecture is a theory that says that accelerated expansion is our local illusion created by the specifics of the universe's form and evolution. This might be a working one, but here we have to assume the energy density fluctuations to be 20 times bigger than we assume them now. And lastly, as always, some people just say that the entire experiment is faulty, the sample is too small, etc. This is unlikely, as we possess further evidence of the accelerated expansion. Unfortunately, I cannot explain all the other pieces of evidence in detail, as it would require a separate presentation again. But the most important one is the cosmic microwave background anisotropies. We regularly remeasure them with ever greater accuracy, and they remain consistent with the cosmological parameters suggested by this study. Some further confirmations which you may read about include baryon acoustic oscillations, the number density of galaxy clusters, the age of the universe, and various gravitational wave measurements. To conclude, these papers paved the way for further advancement in cosmology. The experiment revealed an unexpected phenomenon of the accelerated expansion of the universe, but also estimated the cosmological parameters such as zero curvature, 0.3 matter, and 0.7 dark energy fractions. At the same time, it brought new challenges, such as the enigmatic dark energy. And you may see that there is lots of work to do, both for experimentalists and theorists. The future of our universe, nevertheless, remains obscure. Perhaps all the signs of the Big Bang will eventually vanish, the distant universe will become dark, and the matter will be so scarce that we will hardly notice it. This is also called the de Sitter model of universe. Maybe the universe is doomed to heat death or a big freeze. It is also possible to end up witnessing the big rip, big bounce, or big crunch, perhaps. The truth is, the ultimate destiny of our universe remains uncertain, and only time and continued scientific exploration will reveal its true nature.